theoretical it says, you get a normal, you get a 65% to C, right? You get a C. So we need to no, it's not a difference.
All right, let's do it. What do you want to know?
Can you go over Kepler's laws of motion?
Kepler's laws of motion, sure. Kepler's three laws. Motion. Pull it up here. So, Kepler's first law, as how it says, orbit of the planet's ellipse. Sun is the one focus of the ellipse. Other focus is empty. There's a long axis and a short axis of the ellipse, right? The major axis. Half of that is the very important semi-major axis, which shows up in the third law. But first law is basically one says that the orbit's an ellipse, the sun is the one focus of the ellipse. The second law is the one that says the line from the planet to the sun sweeps out equal areas in equal amounts of time. And I always like to emphasize that if the areas are not equal, then the times are not equal and vice versa. So it has to be equal. If the times are equal, the areas are equal. If the areas are equal, the times are equal. Yes?
How does speed correlate with that, to the speed of the planets?
The speed of the planet correlates with it because of the fact that it implies that a planet goes faster when it's closer to the sun, because it has to keep sweeping out the same amount of area. So when the line to the when the line from the planet to the sun is shorter, the planet has to move a bigger distance along the orbit to make the area swept out still be just as big. So it has to move faster when it's closer to the sun in order to pull that off, essentially. Yeah. And then third law is the one that says p squared equals a cubed. When we use the right units, where the right units are, pick a planet, any planet, and use its semi-major axis and its orbital period as the standard. And then if you did that for any planet, you would find that p squared equals a cubed for any other planet, as long as you express the other planet's orbital period in terms of your reference planet and the other planet's semi-major axis. In terms of your reference planet, I know, let's pick Earth as the reference planet, so that's what we do, and then that means that we measure period of other planets in Earth years. We measure the semi-major axis for other planets in terms of the astronomical unit, the length of Earth's semi-major axis, and then we're good to go with square root of the a cubed.
I was gonna ask, so for Kepler's second law, like with the radius, if the radius from the planet to the sun is shorter, you said that it has to be faster to make up for the, like.
Yeah, because here the planet's distance from the sun is constantly changing as it moves around the sun. Right, so when it's closer, the speed has to be faster. It has to move faster along its orbit to counteract the fact that it's not as far from the sun, so that it can still be sweeping out the same amount of area in the same amount of time. Any follow-ups on that? I always like to try to remember to ask if there's any follow-ups. And then it's like, okay, now somebody else asks. Yes.
Can you go over declination and ascension?
Declination and right ascension.
Sorry,
Yeah, declination and right ascension. So the idea there is that they are very similar to latitude and longitude on the sun, stop, on Earth. there is a way to put latitude and longitude of the sun, but that's not what we're going to say. So on Earth, we specify where points are on Earth by specifying two angles, the latitude and the longitude. The latitude is, as seen from the center of Earth, what would be the angle between Earth's equator, which is defined at latitude of 0 degrees, and the point in question. So on this diagram here, we have indicated some latitude circles, some circles of constant latitude. So for example, everywhere along this circle is at a latitude of 30 degrees north. The angle from the center of the Earth to any point there would be 30 degrees if you would be at the center of the Earth. If you pointed to the equator and pointed to that circle from the center of the Earth, your arm would be swinging through 30 degrees in doing so. And longitude is the east-west direction, and you need to pick a reference. For the latitude, it's the equator. For longitude, we pick the meridian, the circle from the North Pole to the South Pole that passes through Greenwich, England, and that's essentially because when this was decided, England was the world's most powerful country, and so they managed to be defining the zero of longitude. And so anything east of that, we measure angles of east longitude. Anything west of it, we measure angles of west longitude. It's similar on the sky, except that we call celestial latitude declination. So declination is north or south of the celestial equator. And instead of on Earth, where we'll say like 30 degrees north, 40 degrees south, on the celestial sphere we use plus and minus instead. So northern declinations that are north of the celestial pole, north of the celestial equator are called positive, south of the celestial equator are called negative. So this circle right here, this line of declination, everywhere along it is plus 30 degrees declination. Everywhere along this circle is minus 30 degrees declination. And then for right ascension, the equivalent of Greenwich is the March equinox. So 0 hours of right ascension is the March equinox. And we, instead of having east and west right ascension, we simply go along the celestial equator and we divide it into 24 hours because of the fact that the sky appears to spin around us once every sidereal day, once every day with respect to the distant stars for Earth's rotation. And there's 24 hours in that, and so we specify right ascension in terms of hours. And so you might remember on the celestial globe there was markings of 0 hours, 1 hour, 2 hours, so forth, along the celestial equator. And then remember to find coordinates of stars. It was like knowing x and y coordinates on a piece of paper, except that the right ascension is kind of like the x along the celestial equator, and the declination is kind of like the y, up and down, perpendicular to the celestial equator. Does that make sense? Any further questions about that? Yes?
What's the deal with the, like, where you have to subtract the angle from 90?
So yeah, that comes in. I should just grab a celestial globe and hope that you're able to see it well enough to follow it and have it actually come up here. Kind of a vague general question, like remembering, oh, there was something about subtracting from 90. So I'm guessing you're talking about like circumpolar stars and stuff like that. Is that what you're getting at there? Or no?
I don't know, it's like something to do with the meridian.
Well, there's the meridian altitude of the sun. So I think what I would do is to, I'm looking at my phone. So I'm gonna, I wanna say, this is a weird thing, but I just wanna see if your head, because you happen to be right in the line of sight of my phone. So I think your head's okay, all right.
Oh, sorry.
Yeah, that's all. Yeah. I just wanna be sure you're not like blocking people. The audience at home is having their view blocked or something. I think I'm okay here, so, okay. Anyway, that was weird, but anyway. Let me, where did I put that? Yeah, I put some solutions up, and I think I'm gonna pull those solutions out and talk.
Yeah. Yeah, it was in the packet.
In the packet, right,
Yeah.
yeah. So let me project up here the solutions and some figures in the solutions. So, we'll do not that. Just do stop. Yeah.
That was number 6.
Number 6, okay. We'll talk about number 6. Let's see. So yeah, where I was saying things like, okay, it's number 6 I'm getting here. Right, so I was asking things like, I'm trying to see, is this number 6? Well, I'm on my solutions here, it's saying number 5, so I don't know. Anyways, orient your globe appropriately and spin it around the celestial poles, answer each of the following questions, blah, blah, blah. Stars in what range of declinations are circumpolar, i.e. always above the horizon, and what are always below the horizon for, and then we did things like the North Pole of Earth and the equator, and let's do a somewhat trickier one, like at a latitude of 40 degrees north, what range of stars are circumpolar? So I will kind of have this here and hope that you can see well enough. What we did there when you were doing it in class was, okay, in order to represent the sky from latitude 40 degrees north, here's the north celestial pole. I can put it at various angles above the north horizon. For a latitude of 40 degrees north, what angle do I have to put the north celestial pole above the horizon? How's that work? 40 degrees, yeah. The altitude of the pole, its angle above your horizon, is equal to your latitude. So I put the north celestial pole 40 degrees above the horizon, like that. And then the question became, okay, stars in what range are circumpolar? So that means that a star would be always staying above the horizon as the sky appears to turn around us due to the Earth's rotation. So for example, if I point to, let's say Beta Cassiopeiae right here, then notice that that star, as I keep my finger on it, is always staying above the horizon. And so the circumpolar stars, the ones in that range, are in kind of a yarmulke on the celestial sphere, like one of those, Jewish caps, so to speak. How big is it? Well, if you look on the globe here, on the celestial globe, the idea is, okay, the pole is 40 degrees above the horizon, so anything within 40 degrees of the north celestial pole will always stay above the horizon. Does that make sense? If you're within 40 degrees of the pole, you'll always be above the horizon. What is the declination of the pole, of the north celestial pole? What is its declination? 90 degrees, right? So if you have to be within 40 degrees of 90 degrees, what range is that? It is 80 degrees within 40 degrees of 90 degrees. Sure. How about 70 degrees? How about 60 degrees? How about 50 degrees? How about 40 degrees? Is 40 degrees within 40 degrees of 90 degrees? No, that's 50 degrees away from it, right? That's where the 90 minus the latitude comes from. say again?
Sorry, where did the 90 come from?
That the north celestial pole's declination is 90 degrees. So
Oh,
the
okay.
question was, what range of declinations? So the pole is certainly circumpolar, it's sitting above your horizon, and it ain't going anywhere as the sky appears to turn around the pole. So the pole is above the horizon. 80 degrees, that's always above the horizon, because that's only 10 degrees away from the pole, and the pole is 40 degrees above the horizon. So the idea is, anything within this circle of declination right here that is within 40 degrees of the horizon, the north horizon, that is within 40 degrees, I meant to say, forget what I just said about the way, that is within 40 degrees of the north celestial pole will be circumpolar. In other words, anything from 50 degrees to 90 degrees will be circumpolar. The bottom of the range is 90 minus your latitude, because it has to be within that angle of 90 degrees of your latitude in order to be circumpolar. So you get 90 minus your latitude. You look at me like, what?
Yeah.
So
Where did the 50 come from? Not, okay.
it came from 90 minus 40.
Okay.
90 minus 40. Yeah, it came from 90 minus 40 because here's the pole 40 degrees above the horizon. This circle right here is the boundary. Every star right on this circle would just meet the horizon and then come back up again.
Yeah.
How far is it from 90 degrees? It is 10, 20, 30, 40 degrees away from 90 degrees.
Yeah.
In other words, it's at 90, 80, 70, 60, 50 degrees. 90 minus 40 degrees is 50 degrees. And that's why 90 minus your latitude is the bottom of the range of circumpolar stars. That all the way up to a declination of 90 degrees is the circumpolar range. So if your latitude was, let's say, 50 degrees, right? What's the range of circumpolar declinations? If we're 50 degrees north, the range goes from, if you're 50 degrees north, 40 to 90, right? Because it's 90 minus your latitude. 90 minus your latitude.
So will we write 40 to 90?
Yeah, you would say 40 degrees to 90 degrees. Because everything in that whole range would be circumpolar. Yeah.
And what's the, when you subtract, is that called
It's just 90 minus your latitude. It doesn't really have a particular name. I mean, I was describing it as like the bottom of the circumpolar range, but that's just me describing it. It's the lower number in the range of circumpolar declinations.
So your declination is 90 minus your.
So it's 90 minus your, it's from, so basically, you know, if I wrote it out explicitly, oh, I have to erase this. Oh no. The range of circumpolar declinations, and this is something, you know, try to understand it, you know, in other words, don't memorize things that you can understand so that you can just figure it out, and then you don't have to worry about forgetting it. Range of circumpolar declinations is going to be 90 degrees minus your latitude up to 90 degrees. 90 degrees is the celestial pole. 90 minus your latitude is as close as you, is basically is as far down as you can go, so to speak, and still be circumpolar. So in my picture here, the idea is, here's the North Pole, the North Celestial Pole, at your latitude above the horizon. So everything within this red circle, everything inside of that will be circumpolar. The North Celestial Pole's declination is 90 degrees. So 90 minus L will be the declination of this red circle right. Everything within L of 90 degrees, in other words, everything starting at 90 minus L will be circumpolar declinations. Yes?
Could you do like a south example?
Yeah, so if it's a south example, all you do is change everything to negatives. So for example, what if we were at latitude let's say 25 degrees south. Okay? What's the range? So first, what's the bottom of the range? Yeah, 90 minus 25 is what? Was 90 minus 20? Yeah, 65, right? You go like 90 minus 20 is 70. So 5 more from that is 65, right? So everything from 65 degrees up to, except there's one thing I gotta fix. We're in the south, so it's minus. Minus 65 to minus 90. If you're in the southern hemisphere, you just gotta make sure you're using minus numbers. So that's the only difference. And now you could get fancy and say it's minus 90 minus your latitude to minus 90 degrees, blah, blah, blah. But I just think, I think it's better to just think of it as, okay, subtract your latitude from 90, and then just remember to put minus signs in front of it if you're in the southern hemisphere, as opposed to, well, let's see, there's 2 formulas I gotta memorize, and one's got a minus sign, and blah, 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 blah. Stop it. Just think 90 minus your latitude, and then remember to make minus signs if you're in the southern.
So really, you don't really need a picture, like, if you think about it.
Right, well, right, so I'll say 2 things. So right, you don't need a picture, but what I'm hoping you don't do is just say, I'll just memorize that it's this formula, and I have no idea where it comes from, but I'll spit it out. In other words, what I want you to do, and it's much better, is you can visualize in your head what's going on, and then, you should be good to go. Visualize what's going on. Any follow-ups on that before I go to Izzy? Okay, yes?
Could you explain why the sun appears to move along the ecliptic over the course of the year?
Yes, it's the same reason why, as I'm looking at you, your head appears in front of different things as I'm walking around you. Because where we see the sun in the sky depends on where we are in our orbit around it. You see my head in front of whatever. If you drew a line from your eyes to my head, it's in front of whatever's behind my head from your line of sight, right? And if you were in a different part of the room, you would see my head in front of something else because your line of sight would be different. And that's exactly what's happening as we go around the sun. It's a simple fact that our line of sight is changing as we go around the sun, and that means we see the sun in front of different stars during different times of the year. So here in this picture, on February 21st, if we drew our line of sight to the sun appears to be in front of the stars of Aquarius. Whereas here on May 21st, the sun appears to be in front of the stars of Taurus, and so forth. So as Earth orbits the sun, we simply see the sun in front of different stars at different parts of our orbit, and in general, we orbit the sun in a plane, and so that causes the sun to follow a path that is the intersection of that plane with the celestial sphere, which means it's a circle, a plane. If I slice this in two with like a saw, I would be cutting out a circle from the sphere. And so that circle that the plane of our orbit cuts out is the ecliptic, and the sun appears to trace that circle around the celestial sphere as we orbit it over the course of the year. Does that make sense?
Yeah.
Okay. Any follow-ups on that? Okay, next. Yes, next.
What would be like a question if asked?
What's that?
Like an example question if.
You mean about that?
Yeah.
I mean, it could be, why does the sun appear to move along the ecliptic, during the course of the year? Or why does the sun appear in front of different stars at different times, or something like that?
So nothing about the signs.
Oh, so first of all, I wouldn't, so I could show you a picture like this, and then I could say, in what constellation does the sun appear on December 21st? I could do that. Certainly, I wouldn't be like, you don't get to see a picture, what constellation is the sun in on August 19th? then what kind of jerk would I be, right? No, I don't expect you to memorize that, that's just silly, that's just. Yes,
I have a question I looked at, it's in the lecture tutorial.
Yeah.
It's page 8, question 4.
which I forgot to bring my lecture tutorial with me, so if you just read it to me, I might be able to figure it out.
So, in 6 hours, will the observer be able to see the sun? If not, why not? If so, in what direction?
Yeah,
Oh, I guess you
what's the context? Yeah.
Not you.
Yeah,
Yeah.
so which page are we on here?
Page 7 and 8.
Page 7 and 8, okay, nice and early on,
It was about like the sun rising.
okay.
Yeah, with the Taurus.
Mm-hmm. Right, so, yeah, okay. So we've got this, so like figure 2 shows a horizon view of what you would see when facing south on this night at the same time as shown in figure 1. So there's Taurus, high in the southern sky. And then which question are you asking?
4.
4.
So I know it's at midnight.
Okay, so in 6 hours, yeah, so that image there was at, facing south that night at, are we supposed to be midnight? I think we are. Yeah, that's gonna be around midnight, okay, yeah, cause you're turned directly away from the sun. In 6 hours, will the observer be able to see the sun? If not, why not? And if so, in what direction would you look to see the sun? So it's midnight, 6 hours later, what time will it be? 6 in the morning. So at 6 in the morning, the sun, it's not gonna be exactly right, but the sun does what at around 6 in the morning? Rises. So, in other words, it'd be reasonable to think the sun could be rising in the east. Now, depending on the time of the year, sometimes the sun rises before 6 a.m., sometimes it rises after 6 a.m. But split the difference, at least we're gonna see a lovely morning glow, or the sun will be a little above the horizon, but there's a good shot it's close to rising in the east as well.
And then like the next questions too, with the
Okay.
constellations.
All right, so then,
Scorpius.
in which constellation will be behind the sun at the time described in chapter 4? Question 4. So what's the answer to that? If it's in Scorpius at the time that the observer is looking there, right? Because notice the line from the sun, the line from Earth to the sun is landing in Scorpius on the opposite side there. So in other words, on this date, the sun is, on this date, it's gonna be like around November 21st. And so the observer on the backside of the Earth here, away from the sun, is seeing Taurus high in the sky, which means that the sun itself, on the opposite side, is in Scorpius. It's in Scorpius. That's the idea. It'll be 180 degrees away. The sun is in whatever constellation you see high in the sky at midnight. The sun itself is 180 degrees away from that. And then the thing is, it's important to understand that in the course of one night, in the course of one day, the sun hardly moves at all along the ecliptic. So unless you're right where the sun is about to move from one constellation to another, if the sun is in if the sun is in Scorpius at midnight, it's also in Scorpius at noon, and at 3 in the morning, and at 9 in the morning. It's in Scorpius all day long. The only time that changes is right when it's about to move into Ophiuchus. Then, okay, it might be, well, at 6:42 in the morning, the sun crossed the official astronomical boundary between Scorpius and Ophiuchus. But most days, sun's in the same constellation the whole day long. And for many days before and after that. Just when you're in the border between switching constellations might that change. But I'm not gonna
I
need
think the
enough.
wording just kind of confused me on.
Yeah.
how it was
Are you okay with it now?
Yeah.
Okay.
Yeah.
Thank you very much. Yes.
Could you go over the phases of the moon just quickly one more time?
Okay, sure. Yeah. So, how how quickly? I mean, how, you know, how,
In a sense, like enough for us to be able to answer a question.
well, okay,
Yeah.
so, I'll say a couple of things. So, one kind of question I might want you to be able to answer is, if I showed you a picture of the moon, could you tell me what phase you were looking at? Okay, so that would be a possibility, right? So would you recognize a crescent moon if you saw one versus a gibbous moon, for example?
I think so.
You think so?
Yeah.
Okay, right? So, new moon, what's that look like?
You can see it.
Yeah, it's just black, you don't see anything. Full moon, what's that look like?
It's just. the
Oh,
half
there,
side of it.
the half side's lit turns over, right? What about first quarter and third quarter?
First quarter is, if I'm looking at it, I'd be able to see it like this.
Yeah, it's a half
Half
moon,
moon.
right? What about third quarter?
And the third quarter is towards the end, it's like half the
It's
crescent.
another half, no,
Oh,
no.
okay.
Quarter phases are both half moons, okay? But as seen in northern latitudes, remember that, well, let's look at it this way. Okay, so suppose that I am facing south right now, okay? And so if I'm facing south, which way is east? To my left or my right? I'm facing south, which way is east? To the left, so that's east, okay? That's west, right? So, the waxing phases are the ones that can be visible at sunset, because the waxing phases are east of the sun in the sky. They're towards the east of the sun in the sky. The waning phases are the ones that we can see at sunrise, not just at sunrise, but in other words, if it's sunset and you see the moon, it's a waxing phase. If it's sunrise and you see the moon, it's a waning phase. The waning phases of the moon are west of the sun. So let's suppose let's suppose it's sunset, okay? I'm facing south, it's sunset. How do I point to the setting sun? Do I point like this, or do I point like this? The setting sun, setting sun. So it's the west, right? Sunset's in the west, right? So there's the sun over there. The sun's providing the light, okay? The sun's what's lighting up the moon. So, which of these could be correct? I could see a crescent moon that looks something like that, or I could see a crescent moon that looks something like that, given that the sun is over there on the right, because it's setting over there. Which of these is the possible way that the moon could be lit? It's got to be this top one, right? Because the sun's providing the lighting, so it's going to be lighting the right half of the moon when the sun is on my right. It has to be the right half of the moon is the one that I'm seeing lit. So the waxing phases, as we see it, have the right half, have the right side lit. So in other words, this is going to be a waxing crescent. Because I can see it at sunset, and the sun is over there on my right if I'm facing the moon, because I have to look to the southern-ish part of the sky, the southern half of the sky, in between east and south and west is where I'll generally see the moon here. So it'll be the right half that I see lit by the sun over there. Waning phases I see at sunrise. So here's sunrise over here. This is very, not precise drawing I'm doing here. So there's the sunrise. So if the sun's rising in the east and I'm seeing a waning phase of the moon, well, the light's coming from the left, so it's the left side of the moon that is lit, as seen from our latitudes, as seen from northern latitudes. So in other words, if I show you a picture and it looks like this, that's a waning crescent. If I show you a picture and it looks like that, waning gibbous, right? That would be waning gibbous because it's the left side that is lit. And then, what am I trying to say? For the quarters too, right? In other words, if it's first quarter, it's the it's the right half that's lit. Third quarter is going to be the left half. So waning phases is the left side is the lit side, and then waxing phases, the right side is the lit side, as we see it. Yes?
And like, the packet, I'm just trying to remember, so when you draw the circle and there's different phases of the moon, is the new moon, the south or north part, when you're looking at it from, like, kind of talking about? It's like, the sun is shining from this angle to this angle, and there's different directions. Like,
Yeah, I think, but so what phase it is depends on where it is in relation to the sun in the sky.
Yeah.
So when you've got a new moon, the sun and the moon are essentially in the same direction from us, and that's what makes it a new moon. Mhm. Yeah, we can go over some of those, moon phase exercises if people want to. Yes. So that's it. So, and you were asking, yeah, okay. Anything else about like this stuff? Okay, go ahead.
Explain that, precession of the, time.
Precession of the equinoxes. Sure. So let me get a model here. This is remember that day I wasn't able to be here because of going, so it cost me being able to do this. So let's do it now. Let me go grab a model here. Okay, I have here a model of how precession works. So this is very heavy because it's got an iron yoke in it that's hidden from view. And it's going to act like a top. So this arrow here is supposed to represent Earth's axis of rotation. So it's nicely pointing out the direction of Earth's axis of rotation. If Earth isn't spinning, so the real Earth is pulled on by the gravity of the sun and the moon. My model here is pulled on by the Earth's gravity, but the effect is the same. If Earth isn't spinning and I tip it like this, the center of mass is below this pivot point right here. And what that means is this thing will act like a pendulum. I tip it and it just goes like that. But watch what happens if I spin it. So I will spin it around in the same direction Earth is spinning. And when I let go, I'm trying to get it as smooth as I can here. When I let go, watch what it does. See the way it wobbles like that? And if you played with a top when you were a kid or whatever, you've seen tops wobbling. That's precession. And Earth's axis of rotation precesses because Earth's equatorial bulge is pulled on by the gravity of the sun and the moon. So here is, so the Earth, it's solid, but nothing is perfectly rigid. And so if I were to spin a water balloon rapidly, it would bulge out at its equator. Does that make intuitive sense to you? Earth, too, actually bulges at its equator. The equatorial diameter of the Earth is a little bit bigger than